air standard cycle. Air standard cycle we discussed in 4th semester. So again we have to discuss this air standard cycle. So this is a theoretical cycle, and based on this the analysis of the IC engine, it may be petrol engine or it may be diesel engine, can be done with the help of air standard cycle. And in air standard cycle we discussed that the first is the Carnot cycle, which has got no any practical application, but this is a totally ideal cycle that is for maximum efficiency cycle. But for practical purpose we will discuss the Otto cycle, which is applicable to spark ignition engine, or this is also spark ignition cycle, SI, spark ignition. And also we will discuss about diesel cycle. The cycle, air standard cycle used is diesel, and this is applicable for compression ignition engine, and this is also known as compression ignition cycle, CI. And this is for diesel engine. Generally this type of cycle is used. One more cycle, that is the Brayton cycle, which we will discuss in the 6th semester, in this semester itself, but that is used for the gas turbine. After these chapters maybe we will discuss about gas turbine, in which the Brayton cycle or Joule cycle, there are two names, Brayton or Joule cycle. These all the cycles we discussed in the 4th semester in the subject thermodynamics. That means the reciprocating internal combustion engines are classified into two main groups based on the cycle. One is spark ignition engine and other is compression ignition engine. So in spark ignition engine the cycle is Otto cycle, and for compression ignition engine cycle used is diesel cycle. So these engines operating on Otto and diesel cycles, this is Otto cycle and this for this diesel cycle, compression ignition engine karone diesel cycle use hoy. There are some assumptions in air standard cycle. First assumption is working fluid is air. That means although for spark ignition and compression ignition engine the working fluid is the product of combustion also, but we assume that throughout the cycle the fluid remain air, and based on this we will analyze the cycle for some practical purposes, and this air is again considered as ideal gas. What is ideal gas? You know, so the gas or fluids which obeys the gas laws are known as ideal gas or perfect gas. And next assumption is all the processes are internally reversible. So reversible process we discussed in the 4th semester. The processes in which can be reversed or bring back to the original state without any effect on the surrounding. That type of process is called reversible process. Another assumption is combustion process is replaced by heat input from external source. In actual practice, the combustion of fuel produces the heat, but for analysis purpose we'll assume that the heat is supplied from some outside source, not inside the engine, for analysis purpose. And also heat rejection is used to restore the fluid to the initial state. So in actual practice what happened, heat rejection is done by the exhaust of the hot burn gases, but for the analysis purpose we will assume that the heat rejection is carried out to the surrounding and the system is brought back to the initial state. That means from 1 to 2, 2 to 3, 3 to 4, again 4 to 1 initial state. That completes one cycle. So for analysis of internal engine cycles, that is also known as the thermodynamic cycle for engines, so it involves the simplification to a real cycle. Say spark ignition cycle is a real cycle, real engine, and that is simplified to one cycle that is called the Otto cycle. And we also assume that a fixed amount of air is used for the working as the floor working fluid, and it remain air throughout the cycle. In actual practice, what happens, this air become gas after the combustion, but we will assume that this remain air throughout the cycle. And also combustion process is not considered for this analysis. During the analysis of IC engine, we will not consider that there is any such process called combustion, because combustion produces the heat and that is the heat addition. But for the analysis purpose, we'll assume that heat is added from the outside source by some other way. And also there is no intake and exhaust process. That means these processes are not considered in the cycle. And also there is no friction between the piston and the cylinder. And also there is no heat rejection not considered. Friction and heat rejection not considered. Heat rejection means heat loss. Any heat loss is not considered. And one is specific heat is independent of temperature. We know that in an spark ignition or compression ignition engine, air or air fuel mixture enters into the cylinder, and that temperature is different temperature, and after burning the fuel the temperature is very high. So in that case the specific heat of the air and specific heat of the gas is actually different, but we consider that this specific heat does not change due to the temperature change. We will consider it to be constant throughout the cycle. Now say this is an actual cycle. We have already discussed that in an actual spark ignition engine, say there is one intake stroke and there are inlet valve and outlet valves. So when the inlet valve is open, the air fuel mixture entered into the cylinder and piston moves from TDC to BDC, and this we call the intake stroke. Similarly, after that stroke, the stroke is called the compression stroke, in which the piston moves from BDC to TDC upwards and both the valves remain closed, and because of this the air or air fuel mixture is compressed inside the cylinder. And after the ignition, the high pressure is developed and that will push the piston downwards, and that we call the power stroke. So we are talking about stroke, not the process. And in the exhaust stroke, the exhaust valve is open, piston moves from BDC to TDC, and the burned gases are thrown out of the cylinder. And this is the actual cycle that takes place inside the IC engine. For example, we are considering the spark ignition engine. Now, in air standard cycle point of view, we consider that the processes are compression process, constant volume heat addition process, expansion process, and constant volume heat rejection process, and that we call the Otto cycle for a spark ignition engine. So there are no valves. When we do not consider that there is any valve. So what happened? The charge inside the air inside this cylinder is compressed when the piston moves from the BDC to TDC, like this. From BDC to TDC it is going and it is compressed. And after the compression, when the piston reaches the TDC, there is heat addition by some external source. Say Q1 quantity of heat is added to the air. This is compressed air. This is already in high pressure. Now if we add Q1 quantity of heat, then that there will be more pressure and temperature, and that will push the piston downwards, and that we call the expansion, in which the piston moves from the TDC, this is TDC, to the BDC. So that we call expansion process. And during this expansion process, the piston comes down to the BDC. Now at this position, when the piston is at BDC, the heat rejection takes place. This we call heat rejection. Say Q2 quantity of heat is rejected to the surrounding, not by any valve operations, not by any exhaust stroke, but the heat is rejected from the system, and that quantity is Q2, and that heat rejection takes place at constant volume. That is why piston will remain in the BDC, and at this position the heat rejection will take place, and this way the cycle repeats. So this is called Otto cycle. The processes involved are like this. Now from air standard point of view, we can draw one PV diagram. So this PV diagram is for spark ignition engine, in which process 5.1 is called, what is the process 5.1? Sorry, process no, stroke. As a stroke you say, what is that stroke? 5.1? Suction. So suction is represented in actual PV diagram for a spark ignition engine. Then process 1-2 is what process? 5 to 1, 1 to T, 2. What is this? Compression. And 2 to 3? Actually this is combustion. Heat addition. But in actual practice we will call it combustion. Due to the combustion, heat is added. Then 3 to 4 what? Is expansion process. Again 1 to 5, what is this process?
Exhaust.
Stroke হিসাবে আমি কি কম? Exhaust stroke কম। আমি যদি stroke হিসাবে কম, 5.1 is suction stroke, 1-2 is compression stroke, 2-3 is ignition as well as combustion, 3-4 is power stroke or working stroke or expansion stroke, and 5.1 is the opening of the valve. Instantaneously the pressure drops from P4 to P1, and 1.5 is exhaust stroke. But from cycle point of view, we will not consider the suction and exhaust stroke. Only the processes are 1-2. 1 to 2, what type of process?
The compression.
Compression. What compression? What type of compression? S is equal to C. What do you mean by this? That means this is isentropic compression. S is equal to C. S means entropy is equal to C. That means entropy remain constant. So process 1-2, exact name is isentropic compression. And process 2-3, sorry. Process 2-3 is what type of process? Process is a bekwa. That already you have said. This is heat addition. And what type of heat addition? This is constant volume. V equal to C. Volume remain constant. V equal to C. After heat addition, there will be expansion. So process 3-4 is expansion. What type of expansion? S equal to C. That means isentropic expansion process. And for process 4 is from PV diagram we can say that this volume remain constant and heat is rejected. So we will call it a constant volume heat rejection process. So from cycle point of view, we will consider these four processes. Process 1 to isentropic compression. For process 2-3, constant volume heat addition. Process 3-4, isentropic expansion. And process 4-1 is constant volume heat rejection. So if we can say this is heat is added, and in this process Q2 quantity of heat is rejected. So that is why it is called constant volume heat rejection process. So this is PV diagram. We can also draw the temperature entropy diagram. This axis is temperature and this axis is entropy. So in this case, process 1-2, in this you can see this is process 1-2 is S is equal to C. S is equal to C. That means S is what? Entropy. That is why entropy is S1 is equal to S2. That means constant entropy. Entropy remain constant during this process. That is why it is called isentropic compression. And process 2-3, from PV diagram we can see what is process 2-3. V is equal to C. Constant volume heat addition. Q, you can also say Q in, heat is added to the system. And process 3-4 is again S is equal to C. That is why this is S3 is equal to S4. That means entropy remain constant. So process 3-4 is isentropic expansion process, opposite of the compression process, isentropic expansion. And again process 4-1, in this case also V equal to C, volume remain constant, and in this case heat is rejected. That is why temperature decreases from 4-1 to T4 to T1. If we look at this diagram, then say what is this temperature? T1. What is this temperature? T2. And say this one, what is this temperature? T3. Again this temperature is T4. So from temperature point of view, if you see from 1 to T2 compression, for any compression process temperature increases. 2 to 3 is heat addition. For heat addition also temperature increases. So 2 to 3 temperature increases from T2 to T3. Again 3 to 4 is expansion. For any expansion process the temperature will decrease, and that is why temperature decreases from T3 to T4. How the temperature decreases? Isentropically. Then again 4 to 1 is heat rejection process. So in this case heat Q is out, heat is rejected by the system. So this is Q out. Q in the process 2-3 and Q out in the process 4-1. So Q in and Q out. These are the heat interaction during the cycle. So this way we can analyze the cycle, and this is called Otto cycle. And from PV diagram we can see that the heat addition takes place at constant volume, and that is why it is called constant volume heat addition cycle. The another name of Otto cycle is constant volume heat addition cycle. Please remember, Otto cycle, another name is constant volume heat addition cycle. Sometimes it is also called constant volume cycle, but that means constant volume heat addition cycle. So what is the characteristic of Otto cycle? The heat addition takes place at constant volume. What are the other processes? There are two isentropic processes. One is isentropic compression, one is isentropic expansion, and heat rejection also takes place at constant volume during the process for 1, and the cycle repeats. Now
The isentropic combustion.
good. Isentropic process 1 is isentropic compression. Compression. So during this process, the air inside the cylinder, not air, only air, air fuel mixer. You forget about air fuel mixer. When we talk about cycle, we only consider what is inside the cylinder, air. So air is compressed isentropically from point 1 to point 2. S is equal to C. Isentropic compression, and S1 equal to S2. So this is process 1, isentropic compression. The air inside the cylinder is compressed from 1 to 2. That means the volume decreases from what to what? V1 to V2. Volume decreases from V1 to V2. And V1 is called the total volume, Vc plus Vs. And distance from the volume between 1 to 2 is called stroke volume or swept volume. And volume, can you call volume decreases V1 to V2. Process 2, 3.
The constant volume heat addition.
Process 2, 3 is constant volume heat addition. Good. Then due to heat addition, what happened? Ki hoy? From PV বা TS diagram पर साइड तुम्हारे क्या 2, 3 की देखा पैसा PV और TS diagram.
The pressure बढ़ी जाए.
Pressure increases from pressure increases from P2 to P3, and temperature increases
from 2 to 3.
T2 to T3. How temperature increases? Can you call processor to lie? Constant, at constant volume. Acha. Constant volume or heat addition hoise. Volume constant rakhile definitely temperature increase from T2 to T3. At the same time, pressure will also increase. That is okay. Now process 3, 4. 3, 4 to can you go process?
Isentropic expansion.
Isentropic expansion. So the air inside the cylinder is at high pressure and high volume. Already we janisu 0.3 is high pressure and high temperature. So if we allow the piston to move, the piston will move from TDC to VDC, and that we call expansion. And the expansion takes place at constant entropy or adiabatically. Adiabatic, reversible adiabatic processes are called isentropic processes. So this expansion takes place adiabatically, and as a result, what happened from PV and TS diagram, you can say what happened. 2 to 3 is V equal to C. Eto bole cha ki hoy? Pressure decrease from T3. You see pressure ki hoise? Pressure P3 to P4 increase hoise na decrease hoise?
The decrease.
Decreases. And what about temperature?
So temperature also decreases.
Decreases from T3 to T4. This is called expansion. And this is also the work done. Any expansion means work is done by the system. Any compression means work is done on the system. So during the process 3-4, piston moves from TDC to VDC due to the expansion of the air from high pressure P3 to P4 and high temperature T3 to T4. And this takes place adiabatically or isentropically. Now process 4-1. 4-1 key process?
The constant volume heat rejection.
Constant volume heat rejection. Yet আমি দেখাব পাৰো, this is Q in and this is Q out. Heat rejection আমি Q out বুলি ইয়াতে ব্ৰেকেটৰ ভিতৰত তোমাৰ লিখিব পাৰা আৰু এইটোত লিখিব পাৰা Q in. And what happened from process 4 to 1 ki PV diagram पर की देखिसा আমি pressure P4 पर P1 ले decreases है and temperature sorry मोर भूल है ना ऐतो P ठीक है सर T4 पर T1 temperature ले decreases है. So constant volume, that is why the name constant volume heat rejection. Otherwise, we can say this is a heat rejection that takes place at constant volume. And the cycle repeats. Once it reaches the position 1, that means original position. The process started at point 1, it goes to 2, then 2 to 3, then 3 to 4, again from 4 to 1, that means back to the original state, and that is called cycle. What is a cycle? A cycle is a combination of processes in which the final state is same like the original state. What is the original state? 1. What is the final state? That is also 1. That means same. V1 temperature like Korea. Now in this whole process, actually this is TDC and this is VDC. So there is a term called compression ratio. What will be the compression ratio? Say RC. RC equal to kiman? Manavjuti, what is called compression ratio? Ki hobo? RC equal to?
Process 1 to 2.
1 to 2. Kimanor pora kiman volume le compression hoise? V1 or para V2. Why not?
Yes, sir.
So compression ratio is always measured in terms of volume. So what volume? Due to the compression, volume decreases. So V1 is initial volume of the cylinder, including VC. Volume including clearance volume. That is called V1. From 0 to V1 means V1. Total pressure, total volume. And V2 is what? The final volume after compression, and that is called compression ratio. Another term is there for expansion ratio. Yet expansion ratio ki hobo? So RE is equal to kiman? 3-4 is expansion process. So what happened in the 3-4? Volume changes from V3 to V4. So expansion ratio is volume after expansion divided by volume before expansion. But you can see V1 equal to V4 and V2 equal to V3. So in place of V4 we can write V1 divided by V2. So in Otto cycle, in this case, expansion ratio and compression ratio are same, but they are different terms. Expansion ratio is V4 by V3, and that comes out to be V1 by V2, and compression ratio is for the process 1, 2, this is V1 and V2. Okay? So this term is very important. Compression ratio, this term is very important. Actually, all these things we discussed in the semester, 4th semester. Volume. A law as a measure. What is that isentropic law? P V to the power gamma equal to constant. This is the law. And from this is isentropic law. And again, there is a law called gas law. What is that? P1 V1 PV by T is equal to constant, or we can write P1 V1 by T1 is equal to P2 V2 by T2, and this we can say P1 V1 to the power gamma equal to P2 V2 to the power gamma by using the adiabatic law. So in terms of that isentropic law you have to apply for that process 1, 2. What is? Because this is an isentropic process. So for process 1, 2, isentropic law can be used. Process 1, 2, and if we apply that law, a dutar pora ami kisu deduction ami korisulu 4th semester, and law is T2 by T1 is equal to V1 by V2 to the power gamma minus 1. Monot porise ne 4th semester bostu kini saba video etao ase tar. T2 by T1 is equal to V1 by V2 to the power gamma minus 1. T4 by T3 is equal to V3 divided by V4 to the power gamma minus 1. Again, what is V3? V3 equal to V2, V1 equal to V4. So this will be V2 divided by V1 to the power gamma minus 1. Or we can write T3 divided by T2, T3 divided by T4 is equal to V1 divided by V1 by V2, V2 whole to the power gamma minus 1. So this is isentropic law. Keneke paisa ei duta bostu combine korile you will get. Eta whole P1 V1 by T1 equal to P2 V2 by T2. Or eta whole P1 V1 to the power gamma equal to P2 V2 to the power gamma. Ei duta equation hol. Say this is equation number 1, this is equation number 2. Here para jodi tumi P2 naikia kori dia, simple simplification class 8 9 or janeke korisila. P2 naikia kori dile temperature and volume or a relation to paba. Isentropic law for the process one 2 is P1 V1 to the power gamma divided by P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Again, the gas law for the process 1 2 is P1 V1 divided by T1 is equal to P2 V2 divided by T2. So from this we can write P1 V1 into V1 to the power gamma minus 1 is equal to P2 V2 into V2 to the power gamma minus 1. So we can write P1 V1 divided by P2 V2 is equal to V2 divided by V1 whole to the power gamma minus 1. And again, from this we can write P1 V1 divided by P2 V2 is equal to T1 by T2. So from these two equations this left side is same, so we can write T1 divided by T2 is equal to V2 divided by V1 to the power gamma minus 1, or we can write T2 divided by T1 is equal to V1 divided by V2 all to the power gamma minus 1. So the law is T2 divided by T1 is equal to V1 divided by V2 whole to the power gamma minus 1, or we can say what is V1 by V2? V1 this one and this is V2, so this is equal to compression ratio RC to the power gamma minus 1. So the isentropic law for this process 2-3 is this one. Again for process 3-4, which is again a isentropic expansion process, process 3-4 isentropic process, which obeys the law PV to the power gamma equal to C. And in this process also we can write the law like this, say T3 divided by T4 equal to V4 divided by V3 whole to the power gamma minus 1. Again V4, this V1 equal to V4 and this is equal to V2 equal to V3, so we can write V4 equal to V1 divided by V2 whole to the power gamma minus 1, and this V1 by V2 already we know that is equal to RC to the power gamma minus 1. So from these two equations, see this is equation 1 and this is equation 2, from this we can get that this T2 divided by T1 is equal to T3 divided by T4, or we can rearrange it like this, T3 divided by T2 is equal to T4 divided by T1. So from this T equation we get, so this is equation number 3 বা 3 process 3-4 karone eto relation hobo. So this is isentropic law. But before that, in this process a cycle jodi ami efficiency uliao, that is called air standard efficiency equal to efficiency formula ki asile W net work output divided by heat input, that is called output divided by input, that is called work efficiency of a cycle. Now what is W net? W net ami paisilo Q in minus Q out divided by talat already Q in ase. So this is efficiency. It can be written as 1 minus Q out divided by Q in is equal to 1 minus heat output or heat rejected divided by heat added. The Q out is in this process Q out, and during this process heat is added. Now during the process 4-1, that process is a constant volume process, and for constant volume process we know that the heat introduction is equal to m, mass of the air, multiplied by CV, specific heat at constant volume, into the temperature difference, that means T4 minus T1, higher temperature minus lower temperature. Similarly, the process 2-3 is heat addition process, which is also a constant volume process. Process 2-3 is a constant volume process, so in this case also Q in equal to M into CV, specific heat at constant volume, into T3 minus T2. So from this we can cancel these two terms, and finally we get this is equal to 1 minus T4 minus T1 divided by T3 minus T2. And if we rearrange this, this is actually, it should be T4 minus T1 divided by higher basic temperature para low temperature to minus koribole T3 minus T2. Now 1 minus T1 common law, T4 by T1 minus 1 divided by here tomorrow T2 common law, it will be T3 divided by T2 minus 1. So this is the formula now. Eto hobo lage hoday higher temperature para lower temperature, because in this diagram T4 is higher temperature, T1 is lower temperature. Now olop agote ami eta formula paisilo, that is ki paisila monot ase ne, T2 divided by T1 kiman paisilo, RC to the power gamma minus 1. Again aru ki hot paisilo, aru ki asile, T3 divided by T4 kiman paisilo, same RC to the power gamma minus 1. So if this is equation number 2 and this is equation number 2, from these two equations we will get T2 divided by T1 is equal to T3 divided by T4. Hoy na baro? Hoy na hoy? Eto ami pahiso from isentropic law je moi kolu agor page eta isentropic law najanile koba. So etuk ami likhibo paru T3 divided by T2 rearrange kori is equal to T4 divided by T1. Just etur pora ami rearrange korisu, cross kori palai T2 to ephale gole tolot jabo aru T4 to ephale gole oporot jabo. So if that is so, this is equal to this, T3 by T2 and T4 by T1. So that means we can cancel this part. So ultimately we will get 1 minus T1 divided by T2. Now what is T1 by T2? 1 minus 1 divided by T2 divided by T1. And this is equal to 1 minus, what is T2 divided by T1? 1 by RC to the power gamma minus 1. So finally we get one formula for air standard efficiency is what? 1 minus 1 by RC to the power gamma minus 1. So this is the final formula we deduce for Otto cycle. It is called air standard efficiency, or in case of an engine we call it thermal efficiency also. Kihor oporot depend kore? Efficiency of Otto cycle depends on what factor? Kihot kore?
So compression ratio.
Compression ratio. So now tell me, compression ratio বেশি হলে efficiency বাঢ়িব নে কমিব? If compression ratio কি? Increase হলে efficiency বাঢ়িব নে decrease হলে?
So increase হলে efficiency বাঢ়িব.
If RC increases, 1 by RC to the power gamma minus 1 decrease hobo. গম পাইছে নে? এই গোটেই টার্মটো RC increase হলে এটো কমি যাব, কমি গলে গোটেই বস্তুখিনি বাঢ়িব. That means efficiency increases if compression ratio তাৰমানে RC ইনক্ৰিজ হলে তলৰখিনি ইনক্ৰিজ হ'ব কিন্তু 1 বাই তলৰখিনি কি হ'ব ডিক্ৰিজ হ'ব ডিক্ৰিজ হলে 1 মাইনাস সামথিং to যদি ডিক্ৰিজ হয় টোটাল to কি হ'ব ইনক্ৰিজ হ'ব so Otto cycle efficiency depends on efficiency as a compression ratio now you tell me compression ratio কি আছিল আকৌ RC equal to what V1 divided by V2 now what is V1 etu V1 sorry etu V2 etu V1 আৰু এইখিনিক আমি কি বুলি কৈছিলো VC আৰু এইখিনি কি কৈছিলো VS so what is V1 VC plus VS and what is V2 V2 is VC so compression ratio is VC plus VS means clearance volume plus stroke volume that means the total volume when the piston is in BDC and what is BDC VC VC is the volume when the piston is in TDC that is also called the clearance volume so this way the efficiency of petrol engine because petrol engine ami keep cycle oporot depend korise boli koisu that is Otto cycle it works on Otto cycle so spark ignition engine or petrol engine efficiency increases with increase in compression ratio